Okay, here's the fun part, I think. Nobody's going to lecture this, and we're gonna do several sections of discussions. And first, we think the most fundamental one is everyone should aware all the typical analytical approaches or methodologies we have developed so far to measure those CO2 parameters, and then what are the advantages and the disadvantages and the concerns, materials you're going to use, how hard you make those measurements, or in some cases relatively easy to make a good measurement out of it, and so I made some tables. So means this is a complete tables, and it's not a guideline for the discussion, but I think that at least for me, it's kind of easy way for me to understand all of the current methodologies in this business. And I fill in some of the blanks, and I leave most of the tables blank. This is what I feel. For example, this is the pH measurements. I feel there are some obvious advantages and disadvantages for two methods we've been discussed so far. And then you saw those methodologies in the lab, and if you're lucky, you have hands to measure those yourself in this week. And so, for example, let's start with a spectrophotometric pH measurement. And I threw a term. This is not my term. This is just in the literature. And I think Michael DeGrampe and Bob Byrne years ago have throw this term in the literature, and it says, yeah.
Can you blow that up just so I can read it?
Oh, sure.
Just project it properly.
Yeah. How do I? It's right here. All right. Okay, so calibration free. This is one of the advantages, at least under the spectrophotometric pH measurement. And what it really means, it doesn't mean that you don't need to calibrate. I mean, definitely you need to calibrate. As Andrew gave a very good instruction on this methodology yesterday, and then you need to calibrate your measurement against some kind of pH standard. In this case, the trace buffer we considered a pH standard. But it really means is that after you calibrate your indicator against the trace buffer or other standards could be, and then you establish the pK constant, the pK constant for the indicator you use as a function of salinity, temperature, and pressure. And then when you really do the measurement for your samples, you don't need to recalibrate those. And then you can just basically use the equation, and then you measure absorbance, calculate the absorbance ratio, and then plug in the equation, and you got your pH. And that Andrew pointed out that there is issues about accuracy, because there is impurity. For example, there's impurity issues for the indicator we've been using so far. There's about 10% impurity. In the lab session I was in, I talked about this to all the folks in my lab, and that's 10% impurity going to give you some color. Okay? Ideally, if that 10% doesn't have a color, it won't be an issue. Because this is really measure the visible spectrum of your sample. And then if that 10% impurity doesn't have the color, you don't have this issue. But unfortunately, that 10% has a color. And different batch of indicator, different manufacturer have different color on those chemicals. So that gives you uncertainty. And then that uncertainty is quite large, 0.01 pH unit, which is not acceptable for spectrophotometric pH measurement, because we talk about the precision of this is on the level of 0.00, I mean, the fourth decimal place. And easily you can get on third decimal place if you do everything as Andrew and Chris demonstrated. So this is a work in progress. So the beauty part of this methodology is that with those, if you already have those PK values calibrated against some standard, when you actually measure the pH, you don't need to calibrate those. The only thing you need to take into account is the drift of your light system, which is the reference at third wavelengths, and then you measure that every time you take a sample, before every time you take a sample, and then build that correction into your calculation, and then you're done. So that's one of the advantages I think may be useful to point out. And for example, for the potential electrode pH measurement, you have, well, definitely it's convenient. It's much cheaper. Most of the time, it's much cheaper to buy an electrode than buy a spec, right? I mean, you can find a lower end spec to take a pH measurement, but not always trustable. I think so far, acceptable spec I'm using, I mean, this by no means is not the final word for what kind of spec you can use, but at least several $1,000s you have to spend for a decent spec to give you a reasonable good absorbance rating to take for the spec. But for electrode, it probably less. I mean, unless you want to buy a hydrogen electrode, but that's probably overkill. A steel chip?
Except for the time in running it.
Oh, okay. All right. So, yeah. So I just throw out some of this, and then if you have questions come up, I'm going to encourage anyone to join the discussion, and then when you speak loudly so that I can type your comments or suggestion into the table. Or if you don't want to follow this, just throw out the idea. I can start a new blank slides, and we can discuss that too. So go ahead. Yeah.
Have you had any issues with particles present in the spectrum?
You mean the
Lots of particles.
particle? Yeah, that's one of the issue we've been. I mean, I didn't talk about it in the lab session, but ideally, you should filter sample, right? But in a lot of open ocean cruises or open ocean measurement, we don't. We just take sample into the lab on the ship, and then temperature equilibrium and take measurement. So, but in estuaries, you should, because there's a lot of particles, especially you have those particles that are going to screw up your reference, the baseline of your measurement, which is the third. And you probably, it's very hard to get a very decent blank measurement. And that's the time you have to really consider suspended material, particles. Occasionally in the past, the experience I had is some bugs get into the glass cell, the optical cell you're using for a pH measurement. And then we had trouble to actually take the measurement because that bug, I mean, it's alive, it's swimming around. Once you add the indicator into it, it's going to screw up your reference, and then you're never going to get the same reference. So how are you going to deal with that? We basically just flag the measurement and say there's a big bug in there. So we cannot trust it. So that happened a lot, actually.
I'd like to make the proposal that probably for ocean acidification measurements and the quality you're likely to need, and I'll come talk about this in the next section, you should not ever consider potential pH.
Okay.
And
what's the reason?
on the other hand, you don't have to do spectrophotometric pH as well as Alex can do it.
Yeah, that's the
You
point.
totally can't.
Yeah.
And so I think we should be thinking about how to make that simpler and recognizing the trade-offs involved. Because the comment made here about calibration-free during actual measurements is, as he commented, not entirely true. But it's so much closer to that the chance of you getting a good measurement of pH goes up by a factor that is quite large. And I think that's why I would make that as a suggestion, and I'd like to hear any discussion people have that, because to my mind, the only reason for using the other are twofold. One is the cost is different. Two is that there's a hope that you can somehow, you can use it for monitoring like a tank sensibly, but then the calibration becomes a little more awkward. You can probably do it on smaller samples at present, when you compare the size of sample that sensibly had to be used on Kim Yates apparatus, which gave you an idea that you're flushing through a 30 cubic centimeter cell all the time to get a good sample in there. So I'd like to hear people's comments on that suggestion.
Can I just ask you to clarify when you say for ocean acidification measurements and recommending the spec cell, do you mean sort of monitoring, like, you know, the progression of ocean acidification in the basin?
Anytime you intend to calculate either what your dissolved CO2, unionized CO2 concentration was, or what your carbonate ion concentration was from the measurements that you were taking.
Okay. So I'll put recommended, right? For, oops. Any other comments, questions?
I'll second Andrew's.
So I guess because we have if we're using the spec method and we're worried about particulates or organisms in the sample, something that just occurred to me, which is less likely to perturb the chemistry of the sample, filtration or centrifugation? Like if we centrifuge out the particles,
Okay. That's
we get a better temperature.
I don't know. I never have that experience, but I filtered samples before, but I never done centrifuge. So.
In essence, the goal is to make sure that your sample doesn't have an opportunity to exchange with air during its handling. This is awkward for filtering. I find it still harder to imagine for centrifuging. But I'm sure it could be done. I think it'd probably be easier just to think about filtering. If you're filtering with the way that Chris indicated earlier, or maybe even using a peristaltic pump to make sure you're passing stuff through in a smooth, even stream, you can probably do it successfully. Centrifuging seems like beating it with a hammer. But I would hesitate. The real answer is nobody's probably tried it.
I didn't try it.
There's no comment about the speed on this table, about how quick they are to run. And I guess it comes down to, how much you're paying your student or your technician, and how many samples you have to go through.
See, I missed the first part. What's the?
The time it takes to run the analyses in each case.
In both cases?
Yeah.
Oh, for the spec, if you do a manual one, I don't know how long you're gonna take for samples. Probably several minutes to fill up a few cells and do a replicate if you want to do that. And then just do a manual run, and then you wait. You put right after sampling, you put in a water bath or some kind of thermostated device to equilibrate temperature, and that will probably 20-30 minutes. And then after that, you want to do your measurement right away. And actual measurement, I would say it's 5 minutes. If I do it, it's probably 5 minutes. But if you have some students may take some time more to do a sample or two. Really doesn't take much time for the spec. Well, uh, I assume you have your equipment set up and warmed up and ready to go. So, which different spec may have different warm-up time. The spec usually you saw in my lab is take about 2 to 3 hours to actually have stable baseline and light source. And your facility, you have to, see what kind of the equipment you're going to have. A lot of the time, the spec will take actually longer than you actually take the measurements for some samples. So, but
You could argue the same is true with the electrode. By the time you calibrate, you get it all ready, you also have to get your samples up to temperature. When you put them in, you actually have to wait for the electrode to stabilize. I don't think there's a significant difference.
How would you draw the line between filtering and not filtering? I mean, if it's in spring waters, maybe yes, but if it's sort of in between, reasonably clean water, but not completely offshore water, wouldn't you introduce greater errors by busting cells from filtration and from potential gas exchange?
yes, that's why I don't filter. Usually we don't filter samples.
The trouble with all of this is that we have a speculation about what we think might happen. There's almost no experimental evidence one way or the other. It's people's fear leading them to certain behaviors rather than people's knowledge guiding behaviors. So try it. See what the difference is. We're learning this and it's growing. And as it grows, we're spreading the information through the community. But there's not enough information about all the kinds of samples you're going to encounter for us to make blanket statements in this, but rather say that these are the things that concern us and these are the kinds of tests you could do to decide. Because if you can reliably filter a sample, then probably you'd want to filter it anytime it doesn't look like a really clear water. But if you can't reliably filter a sample, probably you try to avoid filtering it, except in extreme occasions. Work out with some simple experiments you design how you do it, because the point is not just, one of the points is can it be done? But the other, and probably more important, is can you do it?
Just a point on filtration, knowing how most people are familiar with filtering for chlorophyll, for example, with vacuum filtration, we found it's entirely inappropriate to even consider a vacuum filtration for pH measurement. So it has to be something with a syringe or that type of filtration.
I would certainly use pressure filtration, and I'd use pressure with more seawater. That's why we filter with a peristaltic pump.
That's what I did once. Or
Could you tell us what people use right now for the culture experiments? Whether
No.
they use a pH meter or
I can't.
Yesterday,
JP.
I wanted to comment on, I would answer the question and also comment on Andrew's suggestion that the potentiometric pH shouldn't be used any longer. For perturbation experiments, as I will tell tomorrow, there is a way to do control experiments is to use pH stats. That is, you have some way to measure the pH, and then you have
just
a
go
control
on
system
the
which
DIC.
injects either
More fun to it.
CO2-free air or acid or base, depends on the experimental setup. So the goal is to maintain pH at a certain level. And most people use pH electrodes to do that. I know that one of you is using spectrophotometric pH, but I have not seen a publication using spectrophotometric pH to control the pH of an experimental setup.
What?
So,
Stay here.
Yeah.
so does that answer your question? Yeah. So I think pH electrodes are still useful for doing perturbation experiments to control your experimental setup, But clearly, that's what we do. We use pH electrodes sometimes for doing theropod work, for example. But then to characterize the carbonate chemistry, we sample for DIC and total alkalinity, and then we do the carbonate chemistry. We don't use pH, potentiometric pH to do the carbonate chemistry description.
Okay, all right. Do you want to? Okay.
If he wasn't going to say
Yeah.
I
Yeah.
would second that. I mean, that is likewise the way I've done it in the experiments I've been involved with. And to rise to Andrew's bait, I think his suggestion is a very good one. I mean, to me, you know, I have not made spectrophotometric pH measurements, but I also know that I have shied away from using my potentiometric measurements for calculations because I just knew that they weren't up to the task. And from what I've seen so far this week, it seems to me that readily doable spectrophotometric measurements are up to the task of characterizing the carbonate chemistry. So if one goal of this meeting is to let everyone go home with an idea of what's on their Christmas list, then it seems to me like the spec method, I think your suggestion is a good one.
I have a question regarding how to handle varying ionic strengths. So I had been deluded with the understanding initially with spec pH, we didn't have to worry about it like we did with the electrodes. But that's not the case because the PK has a salinity dependent on it.
Right.
So if you're running transects in the northern Gulf of Mexico up into the Mississippi plume, and you want to make pH measurements, how do you handle that?
You want to? You want to?
Yesterday, at one of our sessions, we were talking about that very problem, and one person's idea, Jen, I think it might have been yours, was to test the behavior of your dye, basically make your own standard curve at diluted ionic strength of your escurine water, so that you could understand how your dye was working over the change in matrix.
And a paper doing just that was published a number of years ago from a group in New Zealand, mostly et al. In marine chemistry, where they used thymal blue, I think it was, and metacresol purple, and characterized their dye for use over a wide salinity range in an estuary. Has it been extensively used? No. Has it been well tested? Not yet. But I think that it's beyond saying start it yourself. What you have to be able to ask yourself is, how good did I need the measurement? And how good did I get the measurement? And an assertion of somebody else's paper is not an ideal piece to both of those.
Oh, go ahead, Chris.
This was on the previous topic, and then I'll send it down to you. And I just wanted to third that recommendation, but also say we always use a potentiometric electrode in the field and for any culture experiments because the pH changes so quickly when you throw the organisms in there that you can't measure the spec pHs fast enough to catch some of those changes and make sure you're keeping your system where you need to keep it. So I think we need to be careful about putting those kind of caveats into any kind of discussion or information or literature that we put out on that, just because your system can get thrown off terribly if you don't have a little bit tighter time control on those measurements. And you don't necessarily even need to calibrate your electrodes because you're just looking at that relative change if you're running them alongside of your spec pHs at the same time. So I just wanted to emphasize that just from experience and running a number of these kinds of experiments. And especially depends on the volume of your system. The smaller the volume and the more organisms you have in there, the more tighter you need to watch and monitor those parameters, as opposed to a large system with only a few organisms in there. So just keep those things in mind.
So to reiterate what Jean-Pierre said, using a potentiometric sensor for tracking variability and possibly in feedback loops for controlling the degree of variability, it's clearly the way to go. And as those sensors get better, it'll get easier and easier. But at this time, if you actually want to say, in this water sample, what is the carbonate chemistry? Use a spec pH if you're using pH at all.
Back to the ionic strength. I think Bob Byrne is working on a paper to incorporate the low salinity range of some indicators like MCP and probably thermal blue. And as soon you should see that paper come out, and you should have a set of some equations. Actually, you can plug it in for your very large change of salinity. What? Bob Byrne, yep. So I just happened to talk to him yesterday, and yes,
Yeah, I just
right.
wanted to add one quick for your information, something that I haven't heard, may have been mentioned from the groups that were going to the labs, but one thing to remember for the spectrophometric pH is that the dyes actually have a fairly narrow pH range over
Right.
which they work properly. So remember that if you're doing, say, perturbation experiments or
Yeah,
something, or
exactly,
you
right.
still use an electrode for outblending measurements because you're covering a whole range
Right, right.
of pHs.
You need a
that goes beyond the
yeah.
optimal ranges for a
Yeah, that-
particular dye. So
yeah,
you
that
need to think about that.
right. Yeah, that's the really thing you have to consider, that if you out of the range of certain indicator, you have to use another indicator. So that is something at extra effort
But
to.
always ask who you're getting that range from. Because if you're getting from people like Alec and Bob, who want that precision that he showed of 0.0004 in a pH unit, that range is quite small. If you say, hey, I'd be happy with a precision of 0.005, that range is quite a bit bigger.
It's all about the color, how precise you can detect the color of your indicator. That's the.
So wouldn't this be true for the pH meter as well, the range at which you calibrate your
Buffer, with your buffer.
Say that again, sorry, I missed this.
The question about the change in the dyes would apply to the pH meter as well?
Alan, if your electrode is behaving perfectly, then a single buffer would, in principle, operate over the entire pH range. What you really have to understand is electrodes don't behave perfectly, but they're not bad. And so that constrains it a little, but people can quite happily use an electrode with smallish errors, 1 or 2%, over multiple orders of magnitude. So I think that 1 or 2%, he shudders, but that's 0.005 in pH.
Yeah, we have to move on. I mean, sorry about the.
Yeah, we need to move on to the PIC measurements
Yep.
and then we could
So,
target.
okay, so the two methodology listed here, IR-based, infrared-based. So you acidify the sample, you add, extract the CO2, and then you measure with the IR analyzer. And I think Chris Landon demonstrated that yesterday afternoon, and then you have someone have a hand on it. And another one, I believe Andrew had the demonstration, right?
No,
You
we
not?
showed a movie yesterday and there's a demonstration today, is that correct?
Oh, okay. So the coulometer, you use a coulometer to do measurement. I mean, the procedure is the same. You acidify samples and you extract CO2. So what are the concerns? I mean, those kind of an expensive device, all of them.
Yeah.
The coulometer is on the order of.
NDIR is probably $40,000 to $50,000 by the time the dust settles.
Yeah.
The kilometer base, similar, could be more.
So they're concerned that whether you can afford to have one in your lab.
Let alone 3.
And that's what I heard in my lab session. And there's actually another one I was working on that using an indicator to actually measure DIC. And it's similar principle, but using different detectors. That is, you acidify samples, and then you incorporate some kind of a membrane, and CO2 across the membrane, react with the indicator, and then you detect the change of that indicator. I mean, the pH change of that indicator, and then you reference to Andrew's seawater, and then you can have your DIC measure. But still, you need a spec. Some engineer to make an optical cell that it works, and that will take some money. So I would say much cheaper than this, but I wouldn't say probably on the half of like $20,000 you can do it, but still a significant amount of money.
We might also widen this a little bit and consider front end, how you actually dose your samples, because there's considerable variation in that. We saw a very simple system yesterday that's kilometer based on the detection side, but when you dose your samples, it's very manual. Whereas there are these very automated systems that are available as well,
Right.
apart from the detection. So you might want to consider that as well.
Yeah. If you do everything manual, you're probably going to end up less, right? I mean, I did a manual run for the indicator-based DIC. It's about just the parts about $10,000, and then you put your time into it, and no automation, just everything. Just use some kind of pump to push you solutions through, and that's it. You don't need engineer. You can do it your way. If you do discrete samples, you can do that way. And for example, colorimeter, I did totally manual run. I mean, I didn't have the auto analyzer. It just take a long time, and then you have to operate very carefully.
Yeah, at this time, there are, to my mind, two companies where you could send money and they would send you an instrument. And I'm sure many of you have these instruments and could discuss their benefits and flaws, and that might be very useful for listeners. These two companies, one Marianda in Germany, that has implemented both a colorimetric system with, I would say, a semi-automated sample handling. That is, you put a bottle in the system, you shove the tube in the bottle, you turn it on, switch, say I'm ready, enter information about the sample, and walk away. I wouldn't walk far away. The other they call under the name Erica, and that essentially is this infrared detection system where you acidify and integrate an infrared peak. Then Apollo Cytec in Georgia also sells an infrared system about the same cost as the German one. The German one, they'll sell you the system, but you have to buy the IR analyzer. The two together would be about $40,000. For 45, you can get one from Apollo Cytec. This is, to my knowledge, and if anybody knows otherwise, let me know, the only places that we are set up commercially to sell you an instrument. But commercially is a little bit of an exaggeration. They don't sell many instruments. They don't have a large sales force, let alone a large engineering staff handling support calls. It's very touching. You get to meet the person who owns the company, sweeps the floors, and bolts the instrument together. And you get as much help as they can give you, but they are only one person.
You mentioned the kind of removing the, well, acidifying the sample and then removing the water using liquid nitrogen and then removing the gas and then measuring the pressure. Why do people do that? Why do people use that system?
The biggest advantage to using that system is if you wish to recover the CO2 gas for making isotopic measurements on the carbon.
Yeah. So that.
Otherwise, the workload involved is so large that all these ones, no matter how much trouble they seem at the time, don't get a look in as being difficult. Yeah. And, 10 years' time, there won't be anybody who remembers how to blow glass sufficiently well to do the repairs you need quickly.
Andrew, do you have any recommendation for OA research, particularly this two method? Are they both okay, or do you think one is better than the other?
If I were characterizing the advantages, disadvantages, Colin, I have to admit for the NDIR, this is advantages are it's quicker for sample and can get reasonable sensitivity on a small sample. There are no hazardous chemicals to buy or dispose of. It's probably, I would suspect, but I haven't seen data on this, more sensitive to the environmental conditions. That is, if the lab temperature fluctuates, you probably get a more obvious contribution to your variance in the measurement for that than you do relative to the kilometer. Well, these are advantages relative to the kilometer. Kilometer you can do with relatively small samples. We typically don't because we want the highest quality of data for the measurements, but we've done reliable kilometer work with 5 mil samples, no trouble. It's just not as precise. The disadvantages of the NDIR system, I don't really know. I'm sure there must be some, but I haven't had experience working with them. I think that one, to my mind, is that the calibration is not as unambiguous as you might have hoped. Chris alluded yesterday to the fact that an NDIR system is sensing CO2. It is sensing CO2 in a cell, and you're pumping gas around that, through that cell. If there's more CO2 in the cell, the signal is not linear. So you have to have some correction to sort of linearize the signal, which may or may not be good. Second, it's integrating over, although we're imagining it, as I said, as integrating a peak like that, like we had thought of with gas chromatograph, which is often the software people have put on this to do that work. You're not. You're actually integrating a lot of that gas stream and you're moving that through. So it's actually a mechanically filtered version of this signal that's also is really what you're dealing with. And then you calibrate it by saying, I put in a carbonate solution. And for that to really be a good calibration, that gas flow and the shape of the peak has to match really closely what is going on for your samples. That's why I think it's going to be temperature sensitive, because when the temperature of the room changes, the flow rates, the viscosity of the water, other things are going to change, such that that peak will change its shape. This, as I said again, is speculation. I've not done these experiments, except very, very simply a long time ago.
Correct for that with a mass flow regulator. You could really do very precise flow rates, sort of.
You can mitigate the effect with a mass flow regulator. The comments I was making assumed you had that. It's still there. It's not as good as you would hope, because that too has a temperature dependency.
Yeah, I had a question. For someone who's just starting up and there's no money to buy any of this instrument, are there some labs that do this, offer the services?
There are a number of groups who are prepared to run samples on behalf of others. We do it. The NOAA group in PMEL do it. I'm sure other laboratories are in exactly this situation. I see Kim saying, we'll take your money. Most of them, I think it's fair to say, this is not their day job. And so the ability for them to handle a workload of samples in a reliable fashion, and this is something I'm going to come to in our next discussion, is not yet there. We might as a community decide that this is something we would wish. Let's defer that discussion, but I will tell you that you will make savings. It won't be as much as you'd hoped. Somebody has to buy the equipment, train the people, practice using it. And that cost is there, whether it's being done in your contract lab or by you.
We typically analyze 1,000, 1,500 samples for other people a year, but we charge, what is it, Dwight? It's
$8 for DIC.
sorry, how much?
For both operating DIC, you're charging $80.
$80. Yeah. I was thinking you want to.
That's a bargain. Get as many done as you can.
I have some information to provide regarding the Erica. We bought one in April last year. I think it was this year, in fact. This year it was the first commercial instrument, and I fully agree with what Andrew said. I mean, it's a small-scale company. It's a one-man show, so you get what you pay for it. That means so there are some software glitches. Also some engineering glitches, but that being said, we are very happy with the instrument. It fulfills what we wanted to have. We have the standard deviation of 4 to 6 micromoles, which is okay for what we want to do. We do perturbation experiments, and that's okay to characterize the various, the various levels of PCO2 that we use. The price, I think it's overestimated in this table because the instrument is 14,000 euros plus the LICOR. I don't know how much the LICOR. We had one, so.
LICOR, yeah, it's,
Another $14,000.
yeah, at least now it's 18 right now.
I thought I had 28,000 as my thing from euros from him. Okay, then.
No, we paid 14,000 euros. So overall, I mean, we
have
have
figured out what it costs to produce it.
overall we have happy customers. It's okay for what we want to do, and I think it has to be said here that many people in this room, I think, are biologists and will do perturbation experiments, and I think the coulometer-based DIC measurement system is overkill for what they want to do.
Probably is worth noting, though, that, I mean, the Rolls-Royce is the coulometer.
Okay.
I think the coulometer can do better than.
And it's a 1930s Rolls-Royce.
Yeah.
So I have a question about IR versus
It
coulometer.
needs care.
Let's think about the inevitable, and we'll think about failure. So how easy is it to diagnose failure in each separate instrument? Is one sneakier than the other when it fails? Or is it like, oh yeah, it's going up in flames. I know it's dead.
What I would say is that you really need to think about this, how you diagnose that you're not getting the quality of result that you should reasonably expect for that instrument. And that's what my whole discussion earlier was about. Failure is straightforward. You're not getting any result, or you're getting something that's totally implausible. There's no carbon in your sample, or there's 5 times as much as you think. 1.005 times as much as you think. It's harder to see, and you've got to be there. Now, I would say, I don't know, people with the infrared can tell me, the coulometer, once you've lived with it for a while, and listened to it groan and moan through its days, you can start to diagnose it quite easily and find out what's wrong. But to a beginner, it's a spaghetti of tubes and valves, any one of which could decide to have a glitch on you right now just out of sheer cussedness.
That's the soma, not the coulometer.
No, that's also that's the vintage. That's the vintage. Now, we've got a problem here, which is that there's this, as Chris is pointing out, there's this mismatch. The coulometer itself is actually fairly good. Occasionally there are glitches with the solution, but that's very rare these days.
Who calls it the coulometer is just the box.
The coulometer is the actual box that looks like it was made by an instrument manufacturer. The front-end sample handling, if all you do is a thing, you put samples in with a syringe, you can get probably a precision of about 4, or uncertainly probably around 4 or 5, day in, day out with a coulometer. And the total cost that you spent on it is probably about $20,000. But you will do, on average, about 30 minutes per sample. That's because you spent a certain amount of time setting it up that morning where you didn't run any samples. You spent more time calibrating it and getting it going, and then you started running samples, and then it's time to go home and dinner. But if you average that over the day, it comes out
we have
about
to
30 minutes.
summarize those tables.
Right.
Yeah.
What might be able to. Okay.
Let's move on to alkalinity. So I listed here 3 actually, because I believe we have exposure during this week, all 3 methodology. There's closed cell, titration, open cell. There's spec. Kim, you have a spec, a TA system here, right?
Yes.
Okay. All right. So you're going to see that in the afternoon, right?
That will be this afternoon, and it actually uses the same spec system that you guys used yesterday for the pH measurements.
Okay. All right. So I listed here. So since we're going to see that. But I don't believe we have closed cell titration for this class.
Since we haven't seen it yet.
I think one of the biggest advantages for us, and especially if you're trying to do these in a field-based system where you've taken your system to someone else's lab and you're trying to bring samples in offshore and run them right away, which you don't have to do because you can store the samples, is time. The spec TA takes, on the order of about 8 to 10 minutes. And other people can comment on the open cell titration methods using electrodes and those sorts of things, but we were running those on the order of about 20 minutes apiece. If nothing went wrong and if they were, the instrumentation was happy, those kinds of things. The reliability has been much better with the spec TAs, just because the pHs are more reliable. We've also done closed cell titrations, which are typically done shipboard. My understanding, we don't do those anymore simply because we've gone to spec total alkalinities. The closed cell titrations were fairly problematic for us. Our biggest problem with them was bubbles in the system. Very difficult to deal with keeping bubbles out of the system whenever you're doing that. And Chris, you might have some other comments to add on that.
Well, yeah, especially with the closed cell, the bubbles in the system, based on volume.
Chris, could you use the microphone?
Oh, yeah, I'm sorry.
Also comment on the accuracy of volume versus weight.
Yeah, well, that's what I was gonna say. When you're doing closed cell, you're using volume measurements instead of weight measurements, which, could be some problems. Also, I would say if you're using a spec TA system, you have the advantage of being able to do spec pH measurements as well, so you can kind of double up that system.
You be able to measure what?
You can use a spec to do TA and pH.
Okay.
So you can kind of double that system up.
So essentially you're saying that unless you want to run a lot of samples, you can get away with 1 spectrophotometer.
Yeah, I'd say to a certain degree. Obviously, with your pH measurements, storage is a problem. So you're gonna be doing your pH measurements first, and store your TA measurements first. Store your TAs for measurements, but yeah, I think that's an advantage for sure. Probably. And again, I think runtime is a big thing. I've done TA measurements all 3 ways, and spec TA for me is pretty rapid.
And you do.
I'd say precision is identical, if not even accuracy.
Would you like to quote figures for your estimates of precision?
Precision, I'd say, is around 1 micromole. Accuracy, obviously, is a little more difficult to say, but using your CRMs, I'd say we're within 2 micromoles.
That's calibrating with the CRMs or not?
Calibrating our acid with the CRM, yes. We do not coulometrically determine our acid concentration.
Andrew, I don't know if you talked earlier about the differences in error that you can get using volume versus weight measurements for measuring your samples out for total alkalinity. Did you comment on that earlier?
Not as explicitly as might help.
Okay. Basically, when you're weighing your sample for doing a total alkalinity, it's much more accurate than doing it with a closed cell volume. Your volume measurements aren't quite as accurate, and that's reflected in the measurement that you get. You can order, and you might know better about how much error you can add by using volume versus weight. We've just strictly gone to weighing samples and don't do any volumetric measurements at all for these.
In my laboratory, weighing samples, we can consistently get medium-term precisions, that is, over a period of 3 or 4 months, of about 0.7 for alkalinity. At sea, with the same apparatus, over, you saw the picture, 2 months, month and a half, we get about 1.5. At sea, we have to do it by volume.
Right, that's right.
But it's still an open cell titration. We're using basically a pipette system for the volume.
Our open cells titrations also take 10 to 12 minutes. And say our open cell titrations take 10 to 12 minutes routinely.
That's good.
Yeah, ours are certainly 10 minutes. We're trying to squeeze it down.
The other problem on the closed cell titrations, just as a note, in the old system, and I don't know, there might be a new closed cell that they're using. The old cell was a piston-based system where you had a closed cell, and then as you add the volume of acid, there's a piston that's driven up. And it works well if you can get all the bubbles out of it, and unless you break your piston. Because if the piston gets broken, then that cell has to be recalibrated based on the volume. And that takes a lot of time and effort. And so there are some other complications just in equipment and doing that closed cell titration.
In terms of broad generalizations, let me just say that people used to use the closed cell titration in order to also evaluate the total carbon from titration data. There are very few laboratories still doing this. The reliability and accuracy of that, I think, is very hard to achieve. And so I would suggest to you that we could probably wipe that column completely out for this discussion.
Good.
Because it's hard to get the equipment, it's hard to use it well, and there's no obvious added benefit. When we developed our version of an open cell titration, which was a modification of things that had been done 60 years before, it really did achieve the NASA mantra. It was faster, it was better, it was cheaper.
Anybody care to comment on the open cell?
How do you manage to do a titration in 10 minutes? Do you follow your stop whatever? Because there is a 6 minutes bubbling time. So you mean that all the rest fits in 4 minutes?
If you use the 6-minute bubbling time, you will find that the rest fits in 6 minutes. Just about. But we have actually carefully tested and optimized that bubbling and squeezed it down to 4.5 minutes. And we actually have 2 cells in series on our thermostat bath line. So that we are washing one cell and filling it while the other cell is doing the titration. And then we're washing that cell and filling it while the other... So these are really 12 and 13-minute titrations overlapped by 3 minutes.
And the other piece of that comes back to your well-trained technician or person running those samples as well. It's really a fine art to recognize when you're reaching those endpoints and watching, even with the spectrophotometrics or he's watching that pH endpoint. And so you're not going to get that for the first probably several months that you're running those samples. That comes after running hundreds or thousands of samples that you get down to those kinds of ranges.
Just
Our way of doing that is completely automated.
Yeah. Our instrument is completely automated once you've got the sample going. And in actual fact, the bad news for anybody working in my lab is the first 3 hours, they didn't get such good data. The next 3 days, they got the best data they're ever going to get. And with luck, they'll get close to that again after more practice. They always seem to get the very best data ever after they've used the instrument for about 1 day. And then it gets worse. And then it gets somewhat better again.
And it takes much longer if it's not automated. It's not 3 hours, it's more like 3 weeks.
Okay, we're moving into our break here, so I think we're going to stop now for coffee.
Just for balance, nobody's talked about the disadvantages of the spec-TA method. Can we just address that really quickly?
Disadvantage?
My understanding of the disadvantages. Sorry. And again, I have only limited experience with it, is that it's the same problem. You had to have the pH dye properly calibrated. And so somewhere that has to be built in to how you do the system. And we haven't come, I think, to a perfect agreement as a community as to the optimal way to achieve that. So the accuracy of this often, even if Chris had coulometrically calibrated acid, that probably would have got him a worse result, because there's probably other errors that are tucked into what he's calling his acid concentration.
It's a one-point titration. It's a one-point titration, so it's the accuracy of that one measurement is extremely important to the accuracy of the overall result. Whereas with the electrode, we typically do 20-point titration.
The cost of equipment is comparable, maybe a little more expensive, but as was pointed out, once you own a spectrophotometer, it's useful for more than this. The size of sample you could use could be significantly less. I don't know how people do this. In my lab, we're typically, if we're talking advanced and disadvantaged, for the very best alkalinity measurements, we're using 100 mil samples. We can use 20 mil samples. The precision is worse.
You mean the?
Our experience is on the spectrophotometric method, the acid addition almost has to be by weight and not by volume, which limits it to laboratory, or at least not on a shelf. Because as Chris said, that one addition of acid is what you're basing everything on, and if you don't have that correct, all bets are off.
Yeah, that's.
And there are other dye issues. You know, there is an impurity issue that still hasn't quite been worked out yet with the dye. And the dyes are pH specific, pH specific for their ranges. So you may need to work with you know, several different dyes depending on what kind of pH ranges that you're analyzing. Of the pH measurements.
So we will be able to continue this discussion in our second discussion session this morning. I won't be talking for anywhere near as long in that part anyway. And we'll try to round up, because it's going to come back to feed into this as you start to say which are the best. What I hope you're recognizing is there isn't a magic bullet. It's still less a store selling them.
Sorry, one last, I guess this can wait up to come back. There are people asking me, how do you do PCO2 measurement with the bottle?
Sure.
And we're going to...
We'll have probably about an hour and 10 minutes total of discussion time available. It's a much shorter presentation.
Oh, you're next one.
Yeah.
Okay.
Okay.